Before we get into Newton's laws of motion, let's look at some basic operations of vectors. And one of those is vector addition. So if we add two vectors a and b, one way to visualize this is to put the tail of the two vectors together and draw a line parallel to vector a and another line parallel to vector b. And these form a parallelogram, and the resultant vector c is drawn between the opposite points of that parallelogram. Now another way we can add these vectors is the head to tail method. So we put the head of vector a on the tail of vector b, and then draw the resultant vector from the tail of vector a to the head of vector b. And similarly, we can add b to a by placing the tail of vector a on the head of vector b, and the resultant vector c is drawn from the tail of vector b to the head of vector a. And we can see that the resultant vector c has the same magnitude and direction. So therefore, vector addition is commutative, meaning it doesn't matter which order we add these vectors. Another basic operation on vectors is scaling. So if we multiply a scalar or a number by a vector, and assuming s is greater than 0, then we either shorten or lengthen that vector. So for example, if we take the horizontal and vertical components of a, as we've done previously in projectile motion, so we'll write the vector in terms of the sum of the horizontal component and the vertical component. And if you multiply this by a number, we're basically scaling those two components. So if s is between 0 and 1, then we reduce the length of that vector, and if s is greater than 1, then we increase the length of the vector. And if s is equal to 1, well, as we can see, the vector is unchanged. Now for a special case where s is equal to minus 1, then basically we're negating the x and y components. And you get the idea for the special case where s is between minus 1 and 0, and s is less than minus 1. So have a think about those cases. Another basic vector operation is subtraction. So here we have vector a minus b, which is the same thing as negating b by multiplying b by negative 1 and adding this to a. So therefore, using the head to tail method, we can put the tail of the negated vector b on the head of vector a and draw the resultant vector from the tail of vector a to the head of the negated vector. Now in contrast, if we subtracted a from b, which is the same thing as negating a and adding that to b, well, as we can see, the resultant vector in this case, which is drawn from the tail of b to the head of minus a, is not the same vector that we obtained when we did this operation in reverse. So therefore, vector subtraction is not commutative, and the order of vectors in the subtraction matters. We can represent vectors in different coordinate systems. So suppose we have this vector f for force, so this same vector can be represented in a horizontal Cartesian coordinate system, as we've seen previously. Now this same vector can also be represented in this oblique Cartesian coordinate system. So it has one component going along the x-dash axis and one component going along the y-dash axis, where I hat dash and j hat dash are the unit vectors along those axes. Now when we look at physical quantities such as force, acceleration and so on, the physical property should not change when we use different coordinate systems. So in other words, the magnitude of the force vector, using Pythagoras' theorem, is the square root of the sum of the squares of its components. And that's also the same if we use the components in the other oblique Cartesian coordinate system. Newton's second law states that the net force acting on a body is equal to the rate of change of its momentum with respect to time. And momentum is mass multiplied by velocity. Now where the mass is constant, then we can take the mass outside the derivative. So in this case, the net force acting on the body is equal to the mass multiplied by the acceleration of the body. And we can resolve this based on the coordinate system we choose. So in Cartesian coordinates, so what we do first is draw a free body with all the forces acting on it. So for example, if we're analysing the block, we isolate it and we draw all the forces acting on it. And when we don't consider the rotations of the block, we treat it as a particle. So in this case, there's only acceleration in the horizontal direction because the net force in the horizontal direction is not equal to 0. So in the vertical direction, the net force is 0, and in general, parallel forces to the velocity vector can change the speed of an object, whereas perpendicular forces change the direction of the object. Newton's first law is a special case of Newton's second law, which states that the net force acting on a body is equal to the mass multiplied by the acceleration of the body. where the mass is constant. Now one special case is static equilibrium, where the velocity of the block is 0. Well, in that case, the acceleration is also 0, and therefore the net force acting on the body is 0. And another special case is where the body is travelling at a constant velocity, and therefore the derivative of a constant is 0, and the acceleration is also 0 in this case. So Newton's first law can also be written as follows in Cartesian coordinates, where the forces balance in both the horizontal and vertical direction. So here if we resolve the tension forces in the cables into horizontal and vertical components, so the vertical components of these forces balance with the force of weight, and the horizontal components of these forces also balance. A 2 kilo block is dragged along a frictionless surface using a massless cable, and a tensile force on the cable has a magnitude of 2 newtons. And we're asked to draw a free body diagram showing the forces acting on the block. So what we have is the force of weight acting through the center of mass, pulling that block downwards, and we have a normal force, which is a contact force that's preventing this block from sinking into the ground. And a tension force on the massless cable is transmitted to the block. So there's only motion in the horizontal direction, and the acceleration is in the direction of the net force. So applying Newton's second law in the horizontal direction, we have the tension force is equal to the mass of the block by the acceleration of the block. So that's equal to 2 newtons. The mass is 2 kilos, so the acceleration of the block is 1 meter per second squared. A person weighs 80 kilograms and steps on a scale placed on the floor of an elevator, and we're asked to find the reading on the scale in newtons if the elevator is accelerating upwards at 4.2 meters per second squared. So if the elevator is accelerating upwards, there's going to be a contact force from the scale on the person, which is the normal force, and a force of weight. So given that the elevator is accelerating upwards, then the normal force is larger than the force of weight. And if we choose our upward direction as positive, well, we have the normal force minus the force of weight is equal to the mass of the person times the acceleration of the person. And the force of weight is mass by gravitational acceleration, and putting that on the other side of the equation, so if you substitute for the mass of the person, the acceleration, and gravity is 9.8 meters per second squared, you'll see that the person is heavier when the elevator is accelerating upwards. Now repeat this process for case B and C, and post your reasoning in the comments. A box with a mass of 3 kilos is attached to a roof by 2 cables, and calculate the magnitude of the forces in both cables. So drawing a free body of the block, we have the force of weight and the tensile forces in both of those cables. So given the block is in static equilibrium, we can apply Newton's first law in the horizontal and vertical directions. So using trigonometry, and in the vertical direction, we obtain the following expression, where we have the force of weight is the mass by gravitational acceleration. And we took our positive directions to the right and upwards. And now you can solve these simultaneous equations for the forces and post your answer in the comments. A friction force is a type of resistive force between an object and a rough surface, and it's a type of contact force that's tangential to the surface, and experiments have been conducted to determine that the magnitude of the friction force is proportional to the magnitude of the normal force, which is a perpendicular contact force. So consider an object that's stationary, then we call this the static friction force. And suppose we want to move this block by applying a tension force on a cable attached to it. Well, we keep increasing this force, and by Newton's first law, the magnitude of the static friction force also increases until we reach the limit of the maximum static friction. And if we keep increasing the force, then the object gains in acceleration because the tension force is going to be larger than the kinetic friction force while the object is in motion. So the object is easier to move when it's sliding. And in this case, the magnitude of the kinetic friction force is also proportional to the magnitude of the normal force using the kinetic friction coefficient. Let's consider the motion of this block along an inclined plane with some angle theta from the horizontal. Well, we can analyze the motion in a coordinate system with an axis parallel to the plane and another perpendicular to the plane. And we can resolve the force of weight into components that are perpendicular to the plane and parallel to the plane using vector addition. And now we can apply Newton's second law along the parallel direction. So using geometry, this angle theta is equal to the angle of the inclined plane. And using trigonometry, where the force of weight is the mass of the block by the gravitational acceleration, and resolving it into the parallel component, we multiply by sine theta. And that's the only force in a parallel direction. And now we can solve for the acceleration of the block. Let's consider a stationary block in contact with a plane that has an angle theta from the horizontal. And we want to find the maximum angle theta where the block begins to slide. And I'm going to choose a coordinate system with a parallel direction to the plane and a perpendicular direction. So by geometry, think about why this angle theta is equal to this one. And if we apply Newton's first law in a tangential direction, where the force of weight is the mass of the block by the gravitational acceleration, you'll get the following expression. And in the perpendicular direction, and solving this equation for the normal force, and recall the definition of the static friction force. And now you can substitute this in the first equation, and cancelling out mg, and doing a bit of algebra, and then solving for theta, and this is the maximum angle of the plane before the block begins to slide. A ball with a mass of 2 kilos is rolling up a frictionless inclined plane, and we're asked to find the acceleration of the ball. So first we draw a free body of the ball, taking the forces acting through the center of mass, because we treat it as a particle. So we have the force of weight and the normal force. And if we resolve the force of weight into components that are perpendicular and parallel to the plane, well, the perpendicular component cancels with the normal force, so therefore the net force is to the left, directed along the incline, and therefore the acceleration is in the direction of the net force. So what we have is the tangential component of the force of weight is mg sine 30 degrees, and that's equal to the mass by the acceleration. And the mass of the ball cancels, and sine 30 degrees is 1/2, so we have A is equal to g on 2, and the mass is given in kilos, so we're just going to assume units of meters per second squared for the acceleration. A 3 kilo ball is rolled up a frictionless plane, and the initial velocity is 10 meters per second, directed along the incline. Find the distance d that the ball travels. So we took the origin at the ball. Now taking a free body of the ball, we find the following forces acting on it. So the force of weight and a normal force. And we can see that if we resolve the force of weight into parallel and perpendicular components of the plane, well, the net force is to the left. So the acceleration is going to act in the direction of the net force. And taking our positive directions as follows, we're going to apply Newton's second law along the parallel direction, where this theta angle is equal to the incline of the plane. And solving for the acceleration, so substituting for the following values, you'll get the acceleration. And to find the distance, well, we know the initial velocity, we know the final velocity when the ball stops is 0, so we can use the following kinematic equation, given the acceleration is constant. Now find the distance by substituting the known values, and post your answer in the comments. A 3 kilo ball is rolled up a plane, and we're asked to find the acceleration at the time instant shown, and assume the following friction coefficients. So taking a free body of the ball, so we have the force of weight, the kinetic friction force, and the normal force. And this angle is equal to the angle of the plane. So applying Newton's first law in a direction parallel to the plane, where we note that the acceleration is to the left, because it acts in the direction of the net force. Now alternatively, you can assume the acceleration is positive on the right hand side, and if you get a negative result from the equation, then you just flip the direction of the acceleration. Now applying Newton's first law in a perpendicular direction, and note that the magnitude of the kinetic friction force is proportional to the magnitude of the normal force. And we use the kinetic friction coefficient because the ball's in motion. So from this equation, you can substitute for the normal force, you'll get an expression for the kinetic friction force, which you can substitute into this equation, and then you'll be able to find the acceleration. And post your answer in the comments. Today we'll look at cables and pulleys, where the cable and pulley system is massless, meaning that if we take a free body of this portion of the cable, which is going to be in tension, well, if the cable is assumed massless, and we apply Newton's second law, so because we've assumed the mass of the cable is 0, then the tension force is uniform throughout the cable. So in other words, if we isolate this top pulley, then the tension force acting on it is uniform, and of course you're going to have reactions at this pin to prevent the pulley from moving. So you'll have a similar configuration on this side, and on this side you'll also have the same tensile force in the cable. So if we take a free body of this pulley here, then this force, so basically we just resolve these forces into vertical and horizontal components. So therefore the force in this cable attached to the block, and these two forces are just Ft in the other cable. And we have a force of weight that's equal and opposite to those three forces to keep this block in static equilibrium. Today we'll look at a special cable and pulley system known as an Atwood machine, which consists of two masses attached to a pulley and is used to verify Newton's law for a system with a constant acceleration. So treating the cable and pulley system as massless, as explained previously, the tension force in the cable is the same. And we expect the heavier mass to accelerate downwards, so the force of weight of this mass is going to be larger than the tensile force. And this smaller block accelerates upwards, so we expect that the force of weight is smaller than the tensile force in the cable. And the acceleration of each block is going to be equal in magnitude. If we apply Newton's second law to the red block, and then applying Newton's second law to the green block, and now we can add these two equations to eliminate the tensile force, and then solving for the acceleration, and now you can substitute this into one of these equations to obtain the magnitude of the tensile force, which I'll leave for you as an exercise. Let's draw a free body diagram for the blocks and the massless fixed cable pulley system components. So if we isolate the components, and because the components of the cable and pulley system are massless, then the tensile force in the cable is uniform. And by applying Newton's second law to this pulley, well, the mass of the cable and pulley is 0, so therefore the tensile force in this cable must be equal to the tensile forces in the upper cable. And therefore this force on the block is also 2Ft. Now note that these pulleys are fixed, so that means if you resolve this force into horizontal and vertical components, then you must have a reaction on this hinge that opposes this tensile force, and also a reaction in this direction. And I'll leave it for you to draw the reactions at this pin also. So on the smaller block, we have a force of weight, and on this larger block, and we expect the lighter block to accelerate upwards. Two blocks are attached to a massless cable and pulley system, and the mass of the small block and larger block are given, and we're asked to find the tension in the cable and the acceleration of the smaller block. We'll take in a free body of each block, where the tension in the cable is uniform, because the cable and pulley system are massless, and the magnitude of the acceleration vector for both blocks is equal. And now applying Newton's second law to the red block and to the green block, and we can add these equations together, and we basically eliminated the tensile force. And substituting the acceleration into one of these equations, which can be simplified as follows. And now you can substitute these numbers to find values for the acceleration and tensile force, and post your answer in the comments. Two blocks are attached to a cable, and we're given the mass of the blocks, and we're asked to find the tension in the cable and the acceleration of the smaller block. So if you just follow the cable which is wrapped around these pulleys, you'll be able to draw the tensile force at certain locations. So think of this like we're taking the free body of each component of the cable pulley system. And therefore the force in this cable is 2Ft, which is the same as the force acting on the block. And if we're taking free bodies of the block, and the smaller block is expected to accelerate upwards. So in this case we have three unknowns, and I'll leave you to apply Newton's second law on each of these blocks to obtain two equations of motion, and the third equation is obtained from the length of the cable. So the length of the cable is y1 plus 2y2, and then plus his constant length of the cable that does not change when these blocks move up and down. So if you differentiate this twice with respect to time, so therefore in addition to the equations of motion of the block, we have a third equation to solve for the three unknowns. Two blocks are attached by a cable and pulley system, and we're given the mass of both blocks, and we're asked to calculate the force in the cable and the acceleration of the blocks, and make the following assumption. So drawing a free body diagram for the blocks, and we expect the heavier block to accelerate downwards, so therefore this block will accelerate up the plane. And applying Newton's second law to the first block, and applying Newton's second law to the green block, and now you can substitute for the force of weight of block 1 and 2, add the equations together to eliminate the tensile force, find the acceleration, and then substitute it into either equation to obtain a tension force in the cable. And post your answer in the comments. The drag force is a velocity-dependent resistive force and derived from the wind pressure. And if we consider the skydiver and parachute a system and treat it as a particle, well, we have this drag force opposing the motion and the force of weight in the direction of the acceleration. And these are example models for drag. So for lower velocities, the drag force is proportional to the velocity, and for faster velocities, this model is more accurate, where the magnitude of the drag force is proportional to the square of the magnitude of the velocity. So we use this first model when the parachute is open. So applying Newton's second law, we obtain the following expression, which is an ordinary differential equation, which we can solve by separation of variables. Now the special condition when the acceleration is 0, or when the system is in dynamic equilibrium, then we obtain a terminal velocity. A skydiver opens his parachute and has an initial velocity v0, and the system, which is the parachute and skydiver, has a mass m. And part A asks us to derive the ODE for the case of linear drag, where the acceleration is proportional to the velocity. Well, using Newton's second law, where the acceleration acts downwards, where the acceleration is the derivative of the velocity, and if you divide through by the mass, we obtain the ODE. Now part B gives us the solution to the ODE, which you can verify yourself using U substitution, and we're asked to plot the velocity versus time. Well, if you substitute for time equals 0, you'll obtain the initial velocity v0. And as t goes to infinity, well, this term disappears, and so does this term, so we obtain mg on k. And this here is known as the terminal velocity. Now show that the acceleration equals 0 at the terminal velocity. Well, if you substitute for the terminal velocity, then these terms will cancel, which means that the acceleration is 0. Consider a particle travelling along a circular path. Well, the velocity is always tangent to the path. So being tangent to the path, we have the tangential unit vector at time t and the tangential unit vector at time t plus delta t. Now if we differentiate this, we obtain the acceleration. And for the special case of uniform circular motion, the speed, or the magnitude of the velocity vector, is constant. And by vector addition, this is d theta, is equal to the angle between those vectors. And this vector is in the negative radial direction. Now if we divide through by dt, this here is the angular velocity. And that can be obtained, and if we divide through by dt, we obtain this velocity, and this here is the angular velocity. And using this relationship, where v equals r omega, then substituting for d theta dt, we obtain an equation for the centripetal, or center-seeking acceleration. If a ball is attached to a string and swung around a horizontal circular path, then we have a force of weight pointing perpendicular to the circular plane. And we have a tension force, and because we're looking at uniform circular motion, meaning that the speed or magnitude of velocity is constant, then there's no component of this force in the tangential or theta direction. So one component of this force is going to oppose the force of weight, because there's no motion in the vertical direction. And one component is going to point to the center of the circle to keep that ball travelling along a circular path. So by Newton's second law in the radial direction, we have the tensile force in the radial direction is equal to the mass of the ball by the centripetal acceleration, where r is the radius of the circle. And in the vertical direction, and then putting the force of weight on the other side of the equation, and you can obtain the magnitude of the tensile force using Pythagoras' theorem. In our previous analysis for uniform circular motion, we derived the following quantities. So the speed was equal to the radius of the circle by the magnitude of the angular velocity, and we had the velocity being equal to the speed in the tangential or theta direction. Now in the case of non-uniform circular motion, the speed is not constant. So when we differentiate this expression, we use the product rule, and we derived this previously for the case of uniform circular motion. And if we're using this expression, we can write this expression as follows. So therefore, if this is the velocity at time t, and this here is our velocity at time t plus delta t, so therefore by vector addition, this here is equal to the change in velocity. And note that the acceleration acts in the same direction as this vector dv. And therefore the acceleration has a component that points towards the center of the circle, and it also has this component which points in a tangential direction. Consider a ball attached to a string and swung around a circular path, which is vertical in this case. So in this case, the force of weight acts in the plane of this circle. And at the top of the circle, the tension force in the string also acts downwards. So using Newton's second law, and a critical speed is obtained when the tension in the string is 0. Now at the bottom of the circle, and again there's no acceleration in the tangential direction, so we're going to have the net force is equal to the mass by the centripetal acceleration. And when we look at kinetic and potential energy, you'll see why the maximum speed occurs at the bottom of the circle. And at this position of the ball, we have the following free body diagram. So if you resolve the force of weight into radial and tangential components, you can see that the tangential component changes the speed of the ball, whereas the normal component changes the direction of the ball to keep it in a circular path. So in this case, the force of weight contributes to both components. And have a go at writing Newton's second law for this case. A 3 kilo ball is attached to a string and swung around in a horizontal circular path with a radius of 1.5 meters. And we're asked to calculate the force in the string if the ball is traveling at a velocity of 10 meters per second. So in horizontal circular motion, we have the following forces acting on the ball. And the vertical component of the tensile force opposes the force of weight, and the radial component keeps the ball traveling along the circular path. And applying Newton's second law in the radial direction, and Newton's first law in the vertical direction, and solving for the vertical component of the tensile force, and now you can substitute the known values to obtain these components, and therefore the magnitude of the tensile force is obtained using Pythagoras' theorem. And post your answer in the comments. A ball is tied to a string and swung along a vertical circular path, and we're asked to find a critical speed to prevent the ball from falling inside the circle. Well, the critical point in a circle is at the top, because that's where the force of weight is pointing in the same direction as the tensile force in the string. And applying Newton's second law, we have the force of weight plus the tensile force is equal to the mass of the ball by the centripetal acceleration. And when the tension in a string is 0, we have the force of weight, which is the mass by the gravitational acceleration, is equal to mv squared on r. And the masses cancel, so we get v is equal to root gr. And calculating this out, we obtain 4.4 meters per second. A car is travelling around a bend with a radius of 20 meters at a constant speed, and calculate the maximum velocity to complete the turn without skidding. So in this case, the static friction force provides a centripetal force to prevent the car from skidding sideways. And the other forces acting on the car are the normal force and the force of weight. So this car is undergoing horizontal circular motion. Now applying Newton's second law in the radial direction, and Newton's first law in the vertical direction, and recalling the relationship between static friction and the normal force. So you can solve this equation for the normal force, where the force of weight is the mass of the car by the gravitational acceleration. And substitute the normal force into this expression for the static friction, and substitute the static friction into this equation. And you'll be able to solve for the maximum velocity for the car to complete the turn without skidding. A car is travelling at a speed of 10 meters per second around a bend, and the road is banked at an angle of 30 degrees. And we're asked to write the normal force in terms of these variables. We're taking a free body of the car and drawing all the forces acting on it, and I've drawn them through the centre of mass of the car for easier visualization. But we know that the contact forces act at the tyres. So if we resolve the forces into horizontal and vertical components, and recognizing that these angles are equal to the banking angle of the road, and applying Newton's second law in the radial direction and in the vertical direction, and now if we multiply the first equation by sine theta and the second equation by cosine theta and add the equations together, well, we eliminate the friction force. And to obtain a friction coefficient, we can use the relationship between the static friction force and the normal force. You can substitute into either one of these equations to obtain a static friction force and then solve for the coefficient of friction. Explain the advantage of banking the road surface of a racetrack. So treating this car as a particle, which is travelling on a banked surface, well, the normal force acts normal to the surface, and the force of weight acts downwards, and the static friction force acts along the road surface. So if we resolve the normal force into vertical and horizontal components, and if we did the same with the friction force, which will look something like this, and if we recognize that these angles are equal to that of the banked surface, then what we get using Newton's second law is the static friction force cosine theta plus the component of the normal force in the horizontal direction, so that will be Fn sine theta, is equal to the mass of the car by the speed squared on the radius of the track. But in the general case where we have a banked road, then we can see that the normal force and the static friction force contribute to the centripetal acceleration. Consider this Atwood machine. So it's effectively a system of a massless cable and pulley and two masses. So taking a free body diagram of the entire system, we can draw the external forces acting on it. So that will be the force of weight in each block. And for this pulley to be fixed, it must have a reaction to prevent it from translating in the vertical direction. Now if we isolate each component in this system, we see the internal force in the cable. And by Newton's third law, every action has an equal and opposite reaction. So the force pairs are always internal to the system of interacting objects, with the same type of force in the pair. So because the cable's massless, we have the same tension force in the cable, and by Newton's third law, we have an equal and opposite force acting at the same point. And again, we have the force of weight on each block, and because this pulley is fixed, then we must have a reaction at this pin. So therefore you can apply Newton's first law, then you can apply Newton's second law, where you can solve for the unknown tension force and the acceleration. State if the following are action-reaction pairs. And recall by Newton's third law that every action has an equal and opposite reaction. So in the first case, the normal force is not the same as the force of weight, so therefore these do not form an action-reaction pair. In this second case, the gravitational force exerted by object A on object B, which is this force, is equal and opposite to the gravitational force exerted by B on A. So therefore these form an action-reaction pair. And in this case, the friction force exerted by the ground on the ball is equal and opposite to the friction force exerted by the ball on the ground. So these form an action-reaction pair. And by the same argument, for this second case over here, this electrostatic force exerted by both objects form an action-reaction pair.